All right, so today we are going to start looking at different types of circuits. All right, so in order to get us thinking about different types of circuits we may be learning about and different circuit designs, here's a warm-up question for you, the viewer. So if you have ever hung holiday lights, you may notice that some lights are burnt while other lights remain on. Part A asks, how does this contradict what we currently know about circuits? So far we only know about series circuits, so what would this contradict about a series circuit? And then B, how could the other lights remain on if some lights are burnt out? You can use the picture as guidance, or you can perhaps think of how we might design a circuit differently in order to circumvent this problem. All right, when you're ready to go, please resume the video and we'll proceed onward. So today we're looking at 8.4 parallel circuits. Announcements, we have a quiz on Monday 4/19. And besides that, nothing new, just make sure you're staying on top of work. So our agenda for today, how can we circumvent broken appliances / issues with series circuits? Specifically, if we have an appliance that's broken, we notice that the rest of the household appliances will still be able to function. So how can we circumvent some of the issues that might arise from a series circuit / broken appliances? What is a parallel circuit and how do they work? And then applications of parallel circuits. And lastly, mathematically modeling parallel circuits. How can we apply Ver charts to a parallel circuit? And how can we use those Ver charts in order to predict specific data within our circuit? Ver chart will follow the same pattern as we follow with series circuits, except with some rules modified. Alright, so we have an inquiry activity here. If you would like to complete the inquiry activity, please go to Google Classroom. If not, please proceed on with the video. So parallel circuits, series circuit. If one part of a series circuit burns out, the rest of the series circuit won't function. So how can we circumvent this? So we can circumvent this by constructing circuits that consist of resistors arranged in branches. These circuits are known as parallel circuits. The advantage is that a parallel circuit can continue to function even if one branch of the circuit is open / non-functioning. The reason being is that even that one branch isn't working, there's still other branches that the electrons can choose to follow to get to the positive terminal, the high potential area of the battery. So a series connection, if we can knock out this one battery right here, all the batteries won't light up. Whereas if we knock out this one battery right here, okay, the other two batteries will still light up because electrons can actually flow through these other two pathways here. It just can't flow through this one pathway. So that being said, here's a think, pair, share to ponder upon with our new knowledge. So if you've ever hung holiday lights, you may notice that some lights are burnt out while other lights remain on. How could the other lights remain on if some lights are burnt out? This is just a review of our warm-up question here to see how far we've come. So take a moment to pause the video if you'd like and answer your question. If not, we'll continue onward. So the secret here is not only do they have different wires that connect different bulbs. So this wire right here connects this bulb and bypasses the other two bulbs. So as a result, these two bulbs are not connected in a parallel branch with this bulb, so they're not going to be affected by this bulb being burnt out. On the other hand, additionally speaking, there's also another parallel circuit inside of the bulb itself consisting of the filament, all right, and what is known as a shunt wire, okay? So there's a wire that runs through the light bulb and a wire that runs past the light bulb known as a shunt wire. If the light bulb burns out, the current will still be able to flow to other light bulbs through the shunt wire. All right, so this is your shunt wire, this is your filament. When the filament burns out, your current will still be able to go through. It will pass through the shunt wire. It will continue to pass through the shunt wire, I've already said, since it will still be passing through even when the filament's there. And as a result, that will keep the light functioning. Now, if the shunt wire does burn out, then every light bulb that is now part of this branch, a part of this wire, is going to burn out as well. And then here's our shunt wire right here. So we have electric current passing through a shunt wire and through the filament. And then when the filament burns out, electric current can still go through the shunt wire. So this is a simplified version of how Christmas tree lights are arranged on your Christmas tree. Is that there are different intertwining wires, there are different parallel branches with parallel branches corresponding to different sections of light. like we see if we go back here, there are wires that connect to this light, and then there's wires that connect to these two lights, and these two lights, the wires connecting to these two lights will bypass this light. And so that's what's happening right here with the parallel branches. You have wires that connect some lights but not others, and bypass others. So we have these parallel branches. And then within each branch there's about 50 lights, according to this infographic here. I'm not sure, I'm not an expert in holiday lights. And what's going to happen is that one light will burn out. If one light burns out, the rest of the lights in the parallel branch can still stay on because of the shunt wire in here. But once the shunt wire burns out, all lights in the parallel branch will no longer be able to function because the branch is no longer closed. So now what we're going to do is we're going to move on to part 2 of exploring parallel circuits. Specifically, we're going to look at the effect that resistors in parallel have on the performance of a circuit. So if you'd like, please pause the video here and continue with part 2 of our exploring parallel circuits activity. So resistors in parallel. So resistors in parallel are quite weird. We would expect that if we added more resistors into a circuit, regardless of its series or parallel, that the resistance would increase and thus current would decrease. But, all right, with resistors in parallel, what's going to happen is that the opposite is going to happen. As more resistors are added in parallel, the total resistance of the current actually drops and current increases. So there's actually an inverse relationship between the total resistance of the circuit and the number of resistors that are there. So as you add more resistors, the overall resistance decreases, and as a result, the current is going to increase. So there's an inverse relationship between number of resistors and resistance, and there's a direct relationship between number of resistors and current. You increase the number of resistors, resistance will drop, and thus current will increase. So why does this happen? This is quite weird. Okay. So the reason being is that as we add more resistors, this actually creates more pathways for electrons to travel along, which increases current through the circuit. If you can imagine it, it's like a toll booth on a road. If you have just one toll booth, that's going to create a good deal of traffic, but if you keep adding more toll booths in parallel, that's going to open up the flow of traffic because that one area of toll booths are able to accommodate more cars per second, and thus traffic is able to flow through a toll booth section much easier. And the same idea happens with electrons, is that the resistors are toll booths. If we add them in parallel, that creates more pathways for electrons to travel upon, and thus the traffic of electrons, aka the current, is able to flow easier through our circuit. Alright, and then this is why I just went over to toll booth analogy. Another thing is the voltage drop across all branches is the same, meaning that if you have two branches, regardless of what's happening in each branch, the voltage drop is going to be the same, and it's going to be equivalent to the voltage provided by the battery. So if a battery provides 12 volts of electric potential, or potential difference, better said, and you have a parallel component consisting of two branches, okay, that overall parallel component is going to dissipate 12 volts of electric potential energy, and thus 12 volts of electric potential energy will be dissipated across each resistor. And I know it's not technically electric potential energy, it's electric potential energy per unit charge. So sue me, physicists, slight misuse of language. All right, so we'll come back to the voltage drop in a second, okay? The last rule that we have is Kirchhoff's junction rule. It states that the sum of currents in each branch is equal to the current entering the branches. So if we have two branches like this, the sum of the current going through each branch is going to be equal to the current going into the branch. So for example, this branch 3 right here has a current of 4 amperes, and this branch 2 has a current of 7 amperes. If we add that together, that's going to be equal to 11 amperes, which is going to be equal to the current that's coming into the circuit. The reason being is that since charge and current are conserved quantities, we can't have current loss in our circuit, so this current right here of 11 amperes must be split up amongst the two branches. However, the two branches will not have equitable amounts of current passing through. The reason being is that current in each branch depends on the resistance of that branch, aka the maxim that you've probably heard in everyday life before: current prefers the path of least resistance. So, like right here, we can see that this path right here has more resistance than this path because there's less current passing through this path than there is through this path. Okay. To give you an idea, it's kind of like if you're at a DMV, because everybody loves a DMV, and you're waiting in line at the DMV, which route are you going to take? Which line are you going to jump into? the line that goes faster or the line that goes slower. You're going to go through the line that goes faster and hence has less resistance. Same thing, if you have two routes that you can take to get to a destination, you're going to go to the route that takes quicker time and thus has less resistance. Same thing for electrons. Electrons are basically just caught in one big traffic jam and they want to get to the positive terminal as fast as possible. Okay? So here's our toll booth analogy. Again, if we add three resistors in series, it's going to clog up traffic, but if we add them parallel, that will increase traffic, or that will increase the flow of traffic since we're able to accommodate more cars per second. And then Kirchhoff's current law, I'm speaking too much here, states that the total current flowing through the circuit is divided up among any parallel branches, aka if we take the current in point B and sum it with point C and point D, it will be equal to the current from point A, like we see down here. All right. Now, why is the voltage drop is the same across each branch of a parallel circuit? So the reason being is that each branch will split and rejoin the same spot, so the voltage drop across each branch will be the same. All right. To give you an idea, if we remember that we can talk about current flow and voltage drops in terms of water. Remember, the voltage drop is like a height drop. We're going from a high height to a lower height, aka from one potential to another potential. Okay. Specifically, okay, is that if our water branches off at one specific height and then rejoins, it's going to rejoin at the same height. So each branch, regardless of what that branch looks like, has undergone the same difference in height and hence the same potential drop. And that corresponds to circuits as well. So same thing that applies for water and gravity also applies for electric circuits as well, that parallel branches will always have the same voltage drop across them. And that will always be equal to the voltage drop across, or the voltage provided by the battery by conservation of energy. So here's a quick check for understanding. Three identical bulbs / resistors, R1, R2, and R3, are placed in a circuit. We ask A, would the bulbs burn brighter in a series or parallel arrangement? Explain your reasoning. B, if arranged in parallel, would adding more bulbs cause the bulbs to burn brighter or less bright? And then C, if arranged in parallel and R1 is greater than R3 and R2, so we're changing the bulbs from identical to non-identical, we ask which light bulb would burn the brightest. Explain your reasoning. Take a moment here to answer these questions, and when you're ready, we'll go over the answers together as a class. So let's look at A here. So would the bulbs burn brighter in a series or parallel arrangement? So in that case, remember, brightness corresponds to how much current is passing through the bulb. So we need to think about in which arrangement will we get more current in our circuit, overall circuit, parallel or series. In this case right here, remember that if we add more resistors in parallel, that's going to decrease the resistance, whereas if we add more resistors in series, it's going to increase the resistance. A decrease in resistance will correspond to an increase in current, so it's preferable that we arrange all resistors in a parallel arrangement. B, if arranged in parallel, would adding more bulbs cause the bulbs to burn brighter or less bright? This is actually tricky, and there's actually a typo in here. I should add in that there's also an option for equal brightness, okay? So the reason for equal brightness is that if we add more bulbs in parallel, that's going to decrease the overall resistance so more current would be able to flow. So that seems like it would make the light bulbs burn brighter. We have more current in our circuit, okay? However, this current must now be distributed amongst more branches, okay? So there's more branches that we have to distribute this current amongst, thus it's going to result in current through each branch remaining the same. So the increase in current is offset by the distribution of that current amongst more branches now. And see, if arranged in parallel and R1 is greater than R3 is greater than R2, they're not identical. Which light bulb will burn brightest? Explain the reasoning. So remember, light bulb corresponds to the current passing through each light bulb, so brightness corresponds to current passing through each light bulb. So if we have these three arranged in parallel and we want to know which branch will be the brightest, we need to think about which branch is going to have the least resistance, aka offer up the path of least resistance. So in this case right here, R2, since it has least resistance, is going to offer up the best path for current to travel upon, and thus R2 is going to have the brightest bulb. R3 will have the second brightest, and R1 will have the least brightest. And then we have another typo right here. This should be I1 instead of I2. All right. So next we come to Wirth-charts and parallel circuits. Okay. So Ohm's law can be used in conjunction with one piece of information about component organized in a chart to determine current, resistance, and voltage drops in any single one component. So recall that in a parallel circuit, the following rules are very useful. Kirchhoff's junction rule, the sum of a current in all branches is equal to the total currents of a circuit, aka charge in equals charge out, charge conservation, and that the voltage drop across each branch is equivalent, the same, by energy conservation. Okay? So these two rules, when coupled to our Wirth charts, can be used to find all information about our circuit. Okay? Now these two rules are different from series circuits, so you need to make sure you distinguish between series and parallel. Now there is also one other way that series and parallel circuits are different, and that is in finding the total resistance of your circuit. In a series circuit, we get the total resistance by adding each resistor together. Easy peasy lemon squeezy. Not so much in parallel circuits. In parallel circuits, all right, our total resistance is given by the following equation. 1 over total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over blah, 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 so on and so forth. So you need to make sure that you add the fractions together individually. That's the right-hand side. And then when you've done that, you still are not finished because you only have the value for 1 over R. What you need to finish to find your total resistance is take the reciprocal of both sides of your equation, which will give you R. All right, and then we can combine that with Ohm's law, our friend and buddy from 8.3, in order to fully analyze these circuits. So let's take a look at some examples here. So example 1, parallel circuits. For the circuit shown at right, consisting of a 120 volt battery and 3 resistors in parallel, determine the resistor current in their circuit and the voltage drop across each resistor. So our keys here is to fill in what we immediately know, including voltage in the voltage column, and determine the total resistance of circuits. Use Ohm's laws to determine the current in the entire circuit, and then use Ohm's law to find the current passing through each resistor. Couple this with Ohm's law and the equation for total resistance and a parallel circuit, and we can solve our circuit. So first thing we need to take note of is our total voltage provided by batteries, 120 volts. And because the voltage drop across each parallel resistor is the same and equal to the voltage provided by a battery, we can automatically fill out the column for the voltage drops of R1, R2, and R3 with 120 volts. Next thing we do is we know that we have 20 ohms, 40 ohms, and 60 ohms for each individual resistor, so we can fill that in for our resistance column. Now, next thing that we can do is we can calculate our resistance, our total resistance, using the equation for total resistance, and we get 10.9 ohms. Notice that the total resistance is less than the resistance of any individual resistor, confirming what we already have learned, that the total resistance should decrease the more you add parallel resistors in. So the 10.9 ohms, if you carry out this problem by hand, you should have 1 over 40 plus 1 over 20 plus 1 over 60, which should give you 0.091. So you're going to get 1 over R equals 0.091, and taking your reciprocal of that will give you 10.9 ohms. So now what you can do is you can apply Ohm's law to each row, since we know 2 entries of each row, to figure out the third unknown entry, the current. In this case, we're going to take V and divide it by R to get I by itself. So V divided by R is going to be 120 divided by 40, all right, or that's going to be 3 amperes, 120 divided by 20, which is going to be 6 amperes, and 120 divided by 60, which is going to be 2 amperes. All right, and then repeating the same procedure, 120 divided by 10.9 is 11. So we filled out our Wirth chart. Now, a quick way to check and make sure that our Wirth chart is accurate is we can apply Kirchhoff's junction rule to see that the total sum of the current in R1, R2, and R3 is equal to the total current that we calculated using Ohm's law. So our predictions are confirmed. We know that this is an accurate chart here. Okay? So now let's take another look at an example here. So for a circuit shown at right, consisting of a 15-volt battery and 2 resistors in parallel, determine the current in the circuit and the voltage drop across each resistor. So the keys, again, fill in what we immediately know, including voltage and the voltage column, determine the total resistance of current, and use Ohm's law to determine the current in the entire circuit. And then use Ohm's law to find the current passing through each resistor. Again, making use of the 2 equations that we're now getting more and more used to. So our voltage provided is 15 volts, so it goes in total column and the R1 and R2, total row and in the R1 and R2 rows. Our resistance of each individual resistor is 22 ohms and 33 ohms. And as a result of applying this equation right here, we're going to get that the total resistance is 13.2 ohms. 1 over R equals 1 over 22 plus 1 over 33. Calculate that in your calculator, and then take the reciprocal, and you'll get 13.2 ohms. Okay? So now we can apply V divided by R equals I to get our current in each row. So 15 divided by 13.2 is going to be 1.14. 15 divided by 33 is going to be 0.45. And 15 divided by 22 is going to be 0.69. And what's actually cool here is we can actually see the confirmation what we would have picked, what we would expect with our branches is that there's more current passing through the branch with less resistance, again showing that mathematically speaking and conceptually speaking, the electrons prefer the path of least resistance. So a quick check we can do right here is 0.69 plus 0.45 equals 1.14. And as a check for understanding here, all right, for a circuit shown at right consisting of a 240 volt battery and 3 resistors in parallel, determine the currents in the circuit and the voltage drop across each resistor. Okay? All right, so take a moment to work on this, and then when you're ready, you may resume the video. So again, with our keys, we fill in immediately what we know, including voltage and voltage column, determine the total resistance circuit, use Ohm's law to determine the current in the entire circuit, and use Ohm's law to find the current passing through each resistor. All right, so again, with 240 volts, we fill out the entire voltage column of 240 volts. With resistance, we fill out the resistance column of 120, 45, and 360, and then taking and then adding 1 over 120 plus 1 over 45 plus 1 over 360, and then adding those together and taking reciprocals gives us 30 ohms as our overall resistance. And then we can do V divided by R to find the current through each component. So the overall current is 8 amperes, and thus when we find our current through R1, R2, and R3, the sum of that should be equal to 8 amperes. So 240 divided by 120 is going to be 2. 240 divided by 45 is going to be 5.33. And then 240 divided by 360 is going to be 0.67. So as a result, 0.767 plus 5.33 is going to be 6, and then 2 added on to that is going to give you 8 amperes. All right, so some things to watch out for. All right, with series circuits, we fill in the current column since the current through a series circuit is the same, and we calculate the voltage using Ohm's law. Whereas with a parallel circuit, we fill out the voltage column since the voltage drop is the same across each branch, and then we have to calculate the current using Ohm's law. Okay, and then remember that for a parallel circuit, the resistance is not just all 3 resistors added together, it is calculated using this equation right here. So that is 8.4. We'll be working on classwork 8.4 for the remainder of class.